Kicking us off with our talks this afternoon is Axel Alpay here to talk about some improvements in the JIT compiling in AdaptiveCpp.
Yeah, thanks, Tom. So I'll start with a statement that I'm hoping that you all are just going to agree with me on, and that is that often performance can be increased by just generating kernels that make more assumptions about the actual execution context in which they are invoked, i.e. more specialized kernels. And as an example, if you build your kernel in a way that it assumes, for example, a certain alignment of pointers that you're passing in, then it might perhaps perform better, but at the expense of generality, because obviously then it's only going to work for that particular pointer alignment. Now you can kind of address this generality problem by automatically generating such kernels at runtime if you have a just-in-time compiler that then just generates the kernel for the alignment that you're passing in this example. In this case, you're changing the trade-off. In this case, the trade-off would be that you can get potentially more performance at the expense of potentially more JIT overhead. In this study, we refer to such specializations, such optimizations as JIT time optimizations. And this is not a new idea and has been explored in the context of other programming models. For example, there are OpenCL implementations that do some of these JIT time optimizations. POCL, for example, specializes the workgroup size in kernels, as far as I know. There's been some work done on OpenMP compilers that rely on JIT-Compilation to generate specialized kernels automatically. But the code patterns between different programming models might diverge, and some JIT time optimizations might even address aspects that are really specific to a particular programming model. So therefore, we cannot directly transfer these results for other programming models to SYCL in a straightforward way. Additionally, implementing such optimization strategies in SYCL can be challenging because of the multi-backend architecture of SYCL. Because of that, we don't really have a well-defined intermediate code representation in SYCL across all of the backends that such optimizations could just be implemented on in general. And also, unlike OpenCL, SYCL is not as inherently designed around JIT. So if you want to implement something like this, then you need to build your SYCL compiler deliberately in a way that is set up for such JIT time optimizations. And these are our contributions: the Adaptivity framework in AdaptiveCpp, which is such a JIT time optimization framework. It is the first framework for automatic JIT time optimizations in SYCL. And it is also a production implementation. So this already is on GitHub, is shipped to users, and it supports CPUs, NVIDIA GPUs, AMD GPUs, and Intel GPUs, and it's implemented completely in a backend independent manner. We also provide a performance evaluation of our solution, and as I'll show you, there's some substantial performance gains involved in this. Often we outperform vendor compilers. Also, the framework can be seen as addressing some gaps in the SYCL specification without actually needing any changes in user code. And many of these optimizations that we propose cannot be easily replicated in standard SYCL, at least not without writing super non-idiomatic or complex code, which you could end up with if you actually try to do this manually without a framework that does it for you. Now, this is, as I've mentioned, implemented in AdaptiveCpp, which is an open source compiler stack that supports multiple programming models, most famously SYCL, but also we support C++ standard parallelism offloading, and recently we've added support for a CUDA dialect as input language. And the interesting thing about AdaptiveCpp is that it is the only SYCL compiler that has a unified host device compiler that generates a unified code representation based on the LLVM intermediate code representation that is then JIT compiled at runtime for all of the backends that we support. Here you can see an illustration. So SYCL compiler goes in, a unified compiler passes this, generates a unified intermediate representation for both host and device. From there, we extract device binary that is then embedded in the host binary. And then this device binary is then lowered at runtime to whatever format is needed: PTX, AMD, GCN, SPIV, whatever. And this is what allows us to implement all of these optimizations in a backend independent manner and then run on all of this hardware. Now, one obvious question that we need to address is how do we avoid excessive JIT compilation overhead if we start to automatically generate specialized kernels? And the rough idea here is that, well, maybe we could design the framework in such a way that at least after a finite amount of kernel invocations or application runs, there's not going to be JIT anymore. So in this kind of thinking, there are two phases. There's first an optimization phase where new specialized kernels are being generated, but then at some point, it no longer does that, and we are in a stable phase where peak performance is hopefully reached. So this means that the application will eventually be free of JIT overheads, such that eventually the overheads can also be amortized by the increased performance. Now, in practice, this is a bit more nuanced, because even once we are already in the stable phase, we may have to go back to the optimization phase. For example, if some pattern in the application changes, maybe the user changes some configuration file that then changes the algorithm that is used, and then we may have to JIT again. So this is only like a rough idea of how it could look like. This is an illustration of what the framework looks like. So the user application invokes a kernel. The kernel invocation is then analyzed by our Adaptivity engine, which then decides which specializations to enable, which optimizations to enable. It generates a hash for this particular configuration and looks up this hash in an in-memory kernel cache. If there's a cache miss there, then it checks persistent on this cache. And if there's also a cache miss there, then it actually starts the actual JIT compilation process, where it then loads the LLVM intermediate representation that is embedded in the application. Then in the first step, applies all of these specializations that it has decided to enable. Then it runs the LLVM03 pipeline, lowers to backend specific formats such as PTX or whatever, and then populates the caches. This persistent on this cache really is crucial, because this is what actually allows you to amortize JIT overheads not only within one application run, but also over multiple application runs. Additionally, certain optimizations need to rely on persistent statistics. I will explain later on which ones those are. And we have what we call the AppDB for that, which is a per application database for metadata on kernels and their usage pattern, where we can store statistical data persistently. Also for users, there is a mechanism that allows them to control the aggressiveness of these JIT time optimizations. And that is what we call the adaptivity level. And we have this ASBP adaptivity level environment variable. If this is set to 0, then basically everything is disabled. The number of JIT compilations is minimized, and it also JIT compiles a whole translation unit at a time to really minimize the number of JIT compilations. If this is set to 1, which is the default, if you clone AdaptiveCpp now, you will run with AL1 by default. Then all the JIT time optimizations are enabled that we expect to typically reach the stable phase by the second kernel invocation. In this case, it also starts to JIT compile every kernel separately. And then you can increase it also further to AL2, in which case it enables additional JIT time optimizations that might even need multiple kernel launches to reach the stable phase. Okay, so what kind of optimizations and specializations have we actually implemented? First one is a fairly obvious one, which is what we call known group size. And it relies on the observation that typical applications often invoke a given kernel with the same workgroup size again and again and again. So we could just specialize the kernel for the given group size as part of adaptivity level 1. And this is implemented by replacing all uses of the group size with a constant in the intermediate representation, asserting to the optimizer that all the local IDs are smaller than the group size, which it might then use this information, and also informing the compiler backend of the group size. And this can lead to a number of benefits. For example, there might be a simplified calculation of simplified calculations involving the group size. Maybe we can free some registers. Maybe we can get better register scheduling in the LLVM backend. Can you achieve this with standard SYCL? Yeah, kind of. There's the SYCL required workgroup size attribute. However, there's one important difference, and that is that the workgroup size attribute requires knowledge of the group size at compile time, which might be less flexible and also not always viable for all use cases, especially if, say, you're the vendor of a SYCL library and you want to leave the selection of the group size to users at runtime as with the regular SYCL API. So in this case, maybe you couldn't use the attribute. The next optimization we've implemented is global size fits in 32. And this is based on the observation that the SYCL APIs for global IDs or ranges rely on 64-bit. Get global ID returns a 64-bit unsigned integer. But in many cases, actually, the global range fits into 32-bit integers. So we could specialize the kernel based on whether the global range that the kernel is invoked with fits into 32-bit integers. And this is implemented by checking whether this is the case. And if so, then we internally implement the built-ins like get global ID, get global linear ID, and so on and so forth, using 32-bit arithmetic. And we also add LLVM assume intrinsic calls to assert to the optimizer and to the LLVM backend that the return values are smaller than the maximum integer. The benefit here can involve simplified calculation of global IDs or ranges. Maybe LLVM backend might generate instructions for smaller data types. This, you cannot get that easily if you just use standard SYCL. You would basically have to re-implement all of these get global ID, get global linear ID built-ins yourself, which would lead to probably fairly non-idiomatic code. And also built-in assume is not guaranteed to exist by the SYCL specification. Oh, and by the way, there was one particular reviewer who was very concerned about the correctness of this optimization. I guarantee you it is implemented in a correct way. Obviously, correctness for these kinds of things is a prime concern. If you have any concerns here, please ask me. The next optimization that we've implemented is what I call local memory specialization. And that is reliant on the observation that the local memory usage typically depends directly on the group size, because in most cases, what users want is they want X bytes of memory per work item, which means that if we can already specialize the group size, well, then we can also specialize the internal configuration, including the range of SYCL local accessor objects. So what we can do is we can hardwire the internals of the local accessor for the actual requested local accessor size. And that could then lead to a simplified calculation of indices in local accessors, save some registers, and so on. This you cannot really do with just standard SYCL, because to do this, you need to know the internal data layout and the internals of the local accessor and modify that. Then we've also implemented alignment specialization. So for a given pointer kernel parameter, the alignment of that data that the pointer points to typically doesn't change, particularly since commonly we pass in pointers to the start of the allocations, not always, but in many cases. And for many GPU backends, the allocations that they return are strongly aligned. They might, for example, be page aligned or something like that. So in many cases, the alignment that you pass in is going to be the same, and it's going to be fairly strongly aligned. So we can just attach the information about the actual alignment of pointer data into the LLVMIR. And that could then lead to potentially vector load stores, better vectorization, and so on and so forth. This you can only kind of do in standard SYCL if you have at least C++20, which you're not guaranteed to have, because SYCL supports also C++17. And then you could, in principle, use SED assume aligned. But again, this requires providing the alignment information at compile time, which may not always be viable, especially, again, if you're a SYCL library, then you don't know what kind of pointers maybe the user wants to pass into your kernels, and then you cannot do this. Next, we've also implemented automatic no alias. And this based on the observation that whether two pointer kernel arguments alias each other typically doesn't change, because that depends on some algorithmic properties maybe. So what we could do is we could detect pointers that don't alias other pointer arguments and then specialize the kernel based on that. And I'll explain later on how we detect that. And if we detect it though, then we can attach the LLVMIR no alias attribute to pointers that qualify for this property. And there are a number of benefits associated with that. For example, we might get reordering of load stores, better memory access patterns, cached loads, better vectorization, and so on. This you also cannot really do with standard SYCL, because firstly, you're not guaranteed to have the restrict attribute. And also, even if you had it, then the restrict attribute, at least in AdaptiveCpp, is dropped actually when you try to capture restrict pointers, because it doesn't because the in SYCL kernel arguments are members of a struct like a lambda function, and there the attribute is basically lost. So how do we detect pointers that qualify for this? It's in general difficult, but there are interesting special cases that we can actually detect. And that is, we could check whether there is indirect access in the kernel with a compiler check. By indirect access, I mean, for example, if you have a tree data structure where additional pointers are loaded from data that other pointers point to. And if we don't have indirect access, and the allocation that a pointer points to is not also pointed to by another pointer argument. So basically all the pointer arguments refer to different allocations, which is a common case. Then we can use this. And how is this implemented? Well, we have this environment variable, SPP allocation tracking, which enables tracking of all allocations that we hand out in a radix tree. And this allows us for every pointer that is passed in to find the allocation to which that pointer belongs to. The compiler check is not yet implemented. So currently this particular optimization is not enabled by default. And this is more of a preview. Although for the benchmarks that I've looked at in this study, this doesn't matter because there this is safe and those benchmarks don't use indirect access in a problematic way. And lastly, what we've implemented is automatic argument specialization. And this is also the only optimization that additionally comes in at adaptivity level 2. And here the observation is that for some applications, some runtime kernel arguments do not change. For example, you might always use the same problem size that you pass in or something like that. And in that case, we could detect argument values that remain mostly invariant and then specialize the kernels for those and hardwire them. Implementing this can require some non-trivial heuristics. So I refer to the paper for details, but the rough idea is to leverage this AppDB that I had mentioned, store some statistical data in there about the relative frequency in which every individual kernel argument value occurs. And then if we find a kernel argument value that appears more frequently than some threshold, and by default this threshold is 80%, then we can specialize the kernel for that particular argument value. And of course, then depending on how this argument is used, there could be a number of benefits. There could be computation simplification, control flow simplification, saving registers, and so on. And this effectively corresponds to using SYCL 2020 specialization constants automatically in the places where it makes sense. So in summary, the AL1 optimizations are carefully chosen and designed such that typically they do not actually increase the number of needed JIT compilations. And this means that if your backend already does JIT, for example, if you have an OpenCL and SYCL backend, then there shouldn't be a fundamental change in the JIT behavior at AL1. The only additional AL2 optimization is this automatic argument specialization, and this is kind of a higher risk, higher reward thing. And also many of these optimizations cannot be replicated easily or at all in standard SYCL. So now for the evaluation part. I've tested this on hardware from 3 vendors, also hardware that is of slightly different age or very different age, fairly recent powerful GPUs all the way to old integrated GPUs. And the idea here is to simply sample a set of hardware that is as broad as possible. And I've looked at various benchmarks from different scientific disciplines, including mini apps like Cloverleaf and Minibute, but also the FFT, NBuddy, RSBench, Mandelbrot, Ising, D/SPH benchmarks from the Hackbench benchmark suite. The performance data that I'm using is the actual performance data as reported by those benchmarks. So this means I'm not just using some profiling tool to get the actual raw kernel runtime. I'm looking always at the host side measured performance, which might also include overheads such as JIT. And the first thing I'm looking at is the overall performance to find out how competitive are we in principle overall by comparing the performance relative to native vendor models. So I'm comparing to NDCC compiled CUDA, a HIPCC compiled HIP, one API compiled SYCL on Intel. And then I've run for this evaluation the benchmarks until the stable phase is reached and no JIT overheads are present anymore. So this is like the what users would get if they run the application for some number of times. And this is what you find then on video. So shown here is the speed up that we achieve over CUDA for the 3 different adaptivity levels. And what we can see here is that higher adaptivity levels generally deliver more performance as expected. And also, if you take the geometric mean of the best AdaptiveCpp configuration, the geometric mean of the speed up, then we find that we outperform CUDA by 30%. On AMD, we find that there are some massive performance gains in some cases. For example, for RSBench, we outperform HIP by 5.8 almost, by a factor of 5.8. And in the geometric mean, we outperform HIP by 44%. On Intel, RSBench failed to validate, so I've omitted the results here. And what we find on Intel is that mostly AL2 has an effect. And here we outperform one API in the geometric mean by 23%. Of course, it's also an interesting question to look at how much each individual optimization contributes. And to do this, I've enabled optimizations progressively in the order as listed here. So we start with 0 optimizations enabled, which corresponds to AL0. And then I've added the first one, which is not group size. And then I've added global size that's named 32, and so on and so forth, as in the order as laid out here. And then what you find is, what you see here is the the speed up that you get by enabling each additional optimization. And the way to read this is that, for example, the second row shows the speed up that you achieve by going from one enabled optimization to two, which would, in the order that was previously laid out, would mean to additionally enable the global size fits in 32 optimization. You would get, for example, 1% speed up on the A5000 GPU. And what we find is that on NVIDIA, almost all the optimizations contribute modestly. So the combination of them all is important for NVIDIA performance. Whereas on AMD, we have this massive 39% speed up when enabling the very first optimization. And this is known group size. So this is primarily responsible for the speed up here. On Intel, the speed up is mostly due to the automatic argument specialization, as we had already seen in the previous plot. So what we can summarize here is that all of these optimizations are beneficial in at least some circumstance on some of the hardware. Now there are a number of other interesting questions that we've looked at, and that is, how quickly does performance converge? What about kernel submission latency due to the additional analysis that we need to do to figure out which specializations to enable? What about JIT overhead? And what about the individual applications? Why are they actually faster? What kind of different code is generated? And for the first three questions, I'm using Cloverleaf as a proxy for the worst case. And the reason why it is interesting for this use case is that it submits many, many short-running kernels. So there's a latency-sensitive component here. And also the kernels are mostly fairly simple and therefore mostly insensitive to optimization. So basically here we are paying the cost, but we are not getting the benefit. So this is interesting to look at for overheads, for example. Okay, and this kind of plot, what is shown here is on the x-axis, you have the number of enabled optimizations. And on the y-axis, you have the application run. And what I've done here is I've rerun the application until no JIT occurs anymore, which means that the lowest cells always show runs where we are in the stable phase, where no additional JIT happens. Whereas the cells above the lowest one always do some kind of JIT. And the numbers that are shown here are the speed up over the very first AL0 run, i.e. the cell in the top left corner. And what we find is that at AL1, across all of the applications, no JIT happened anymore by the second application run. And this is because as expected and as designed, the AL1 optimizations already converged by the second kernel launch. At AL2, we find that across all of the applications, no JIT happened anymore by the third application run. So if you enable AL2, then you might need one additional application run to get peak performance. What about kernel launch latency? Of course, the additional latency, additional analysis to figure out which specializations to enable could add some additional latency. But what we find is if we look at always the lowest cells from 0 optimizations to 6 enabled optimizations, is that there's no noticeable slowdown as we add more of them. And that means that the runtime overheads are typically not expected to be significant for typical apps here. Now, what about JIT overhead? We can also make a statement about that by looking by comparing the first row of data always to the lowest cells, because the first row is going to be the very first application run. So there you always have the JIT. And in the lowest cells, there's not going to be any JIT anymore because this is always in the stable phase. And what we find here is that there is this interesting performance drop in the very first run, where if you go from in the first row from left to right, you go from 1 to around 0.9 on NVIDIA, for example. But actually, this is not due to more kernels being generated, because if that were the case, then you would go further down as you enable more optimizations and more kernels, more specialized kernels are generated. Instead, this is simply due to this one switch in the runtime code object model where we start to JIT compile every kernel separately. And this might actually even be beneficial in some cases. If you have large translation units with many kernels, but you only invoke some of them, then this is going to be better. In this particular case, you're doing more smaller JIT compilations, which happens to be worse in this particular case. But what we conclude here is that the AL1 optimizations are sufficiently carefully selected such that additional JIT generally is not an issue. At AL2, this is more difficult to interpret because, well, I mean, in principle, what you'd need to do is at AL2, you'd need to have some kind of benchmark that actually simulates a user workflow in the sense that it includes things like the application is maybe sometimes also run with different command line arguments and so on and so forth. But this is not how benchmarks are typically structured. So this is kind of a best case scenario for AL2. Now, for the individual applications, this is here only a quick summary. Please see the paper for the full discussion on the individual application results. For some apps like Mini-Butte on NVIDIA, we see basically the ideal expected behavior where performance increases both for more enabled optimizations and more application runs. This high speed up on AMD for FFT that we've seen is due to known group size, where the compiler detects that the actual group size of 64 in this case matches the subgroup size of the hardware, which is also 64, and then it can emit all of the workgroup barriers and replace them with subgroup barriers. On RS Bench, we also have seen a very large speed up, which is due to improved register allocation, also due to non-group size, which substantially reduces register spilling here. And for D/, there was a significant speed up due to the automatic no alias optimization on AMD and NVIDIA, because the compiler actually emits texture loads, cached loads, which actually utilize the texture cache. So in conclusion, the new JIT time optimizations, they can deliver substantial performance improvements. We've seen 30% geometric mean speed up over CUDA, 44% over HIP, and 23% over OneAPI. For some applications, the speed up can be much higher. We've seen in excess of 5x for RS Bench. And especially at AL1, there are few downsides because typically the number of generated kernels doesn't increase. So therefore, typically there's also no additional JIT overhead. This also addresses some gaps or issues in the current SYCL standard. For example, APIs that return 64-bit size T, or the lack of no alias or restrict semantics. And this is also already in production. So if you've used any kind of recent AdaptiveCpp release, then you've already most likely used AL1 at least, and also some of the results that have been presented at this conference before probably also have used some of this work. And of course, in the future, we could improve on this in various ways, for example, with auto-tuning or by integrating with the LLVM PGO, profile guided optimization infrastructure. So there's lots of further opportunities for further improvement here. All right, that's all I have. Thank you.
Thanks for the talk. Does AL2 work for non-fundamental types?
Yes. So nice. Because AdaptiveCpp always decomposes kernel arguments into fundamental types when it passes them in the JIT compiler. Okay. So you always end up with types, with kernel arguments that are scalars, basically.
Okay, thanks.
Could you please go a few slides below to the performance chart?
Which slide? Performance chart?
27, 29.
29. This one?
Yeah. So I'm trying to understand, for example, AMD zero optimization, so AL0.
Yeah.
Why we see such big discrepancy between first and second run?
In the second run, the JIT cache is already populated.
But if we apply no optimization, would it be more reasonable to expect that such applications would be using ahead of time compilation?
Potentially. I mean, there are still advantages to using JIT, for example, the portability aspect of it, because our JIT compiler can seamlessly target all of the backends, which means you get lower compile times because you only need to generate a single device image. And the resulting binary works across all the backends and all of the AMD GPUs and the NVIDIA GPUs and so on and so forth.
Yeah, but you could also generate multiple device images. So I just wanted to point out, it's not a big thing, right? It would just simply change numbers over the first row, but in second row, it would be look the same anyway. I just wanted to note this because I'm working with Blender, and Blender actually target ahead of time compilation as a main way to distribute device binaries. So it was.
I think that for the problem is that there are some backends like AMD, for example, that don't have an intermediate representation for all of the GPUs. So if you wanted to have a binary that is actually portable with ahead of time compilation with SYCL, you'd need to do like 40 compilation passes or 50 or something like that. And I mean, if you want to do that, sure, but this is not what the AdaptiveCpp JIT compiler was designed to handle. Obviously, it was designed to solve such problems.
Okay. Makes sense. Thanks.
What about libraries? So if I have a library and it's used from different applications, do you optimize it per application or
per application? Because the assumption is that different applications may have different patterns in which they use the library, which functions they call in the library. If you're using AL2, then even the arguments that you're passing into the library might matter, right? The values. So then it really makes only sense to do this per application.
Okay, thanks.
Thanks.